Hello, dear students. I am presenting you a video lecture on voltage transfer characteristics of CMOS inverter. So here we will analyze the CMOS inverter circuit and derive the voltage transfer characteristics. This lecture will be useful for the people who are absent for the class when I took CMOS inverter. And if you are having doubts, you can refer to this video lecture and learn. And CMOS inverter characteristics is a very important topic, a very interesting topic too. So I would request everyone to view this video lecture and clarify the doubts that you have. Okay, let us come to the circuit. Okay, this CMOS inverter circuit is well known and it is the basic gate. Okay, so everyone knows this and everyone knows how this works. And we have the PMOS stacked on the top of your NMOS device, and the gates of them are connected together, and the input is given here, and the drains are connected together, and the output is taken here. And then IDSP and IDSN are in the opposite direction, they are equal and opposite. And when Vin is equal to 0, only PMOS is conducting, NMOS is off, this is on. So this path is closed, so I will get VDD here. And when Vin is equal to 1 volt, PMOS will be off and NMOS will be conducting. So this Vout will be pulled down to this voltage, that is the ground voltage. So you will get a 0. So when you give a 0, you will get a 1. When you give a 1, you will get a 0. Okay, and the substrates of both the transistors are connected to for NMOS transistor it is connected to the ground, and for the PMOS transistor it is connected to the VDD, so that the substrate source and the substrate drain junctions are reverse biased. Okay, now let us see the CMOS inverter circuit diagram in detail with the voltages. Okay, we refer to these voltages with suffixes N and P. Okay, N refers to NMOS transistor and P refers to the P transistor, PMOS transistor. Okay, and we have this one, Vin is given between the gates of both the transistors and between the ground. Okay, so between this gate terminal and the source terminal of the N transistor, we can call it as VGSN. So VGSN is nothing but Vin. Similarly, VDSN. Okay, between B and S of the N transistor VDSN, we have Vout. Okay, and between these two terminals, we can call this as SG because S is in the higher potential, so SGP. Okay, and similarly, we have VSBP. Okay, so now the relationship between these voltages and the input and output voltages are given in the next slide. Okay, initially it is the first point is IDSN is equal to minus IDSP and VGSN is nothing but Vin. Okay, but VGSP is equal to minus VSGP. Okay, so VSGP is nothing but VDD minus Vin. So minus VSGP will be Vin minus VDD. So that is equal to VGSP. So VGSP is nothing but Vin minus VDD. And then VDSN between the source and drain of your N transistor, you have the output voltage VO. Similarly, for the P transistor, it is the reverse. You have a minus sign. Okay, so VSD is nothing but VDD minus VO. So VDS will be VO minus VDD. So these are the relationship between the current and voltages in the circuit diagram. So we have VGSN is nothing but Vin, VDSN is nothing but Vout, but VGSP is Vin minus VDD and VDSP is Vout minus VDD. Okay. Okay, so remember these relationships. Now these are the relationship between the voltages and the three regions of operation in the CMOS inverter. Okay, we know that N and P transistors, they work in three different regions: the cutoff region, the linear region, linear or resistive region, and the saturation region. Okay, you know the conditions also. So if your input voltage, that is the voltage between the gate and source, is less than the threshold voltage, the transistor will be in the cutoff state, and when VGS is greater than VT, it will come to the linear state, or it will be start conducting, and it will obey Ohm's law for some portion, which is called as the resistive region or linear region. After some time, it will enter the saturation region, and the current will become constant. Okay, it will act as a constant current source. So this one we have already studied in the characteristics of N transistor. So now for NMOS and CMOS, you have similar conditions. So for NMOS, the cutoff condition is VGSN is less than VTN. And for linear, you have two conditions. VGSN must be greater than VTN, and VDSN must be less than VGS minus VTN. Okay, so now these are the two conditions, and for saturation, it is just the reverse. It should be above, the input voltage should be above threshold voltage, and this condition is reverse. VDSN must be greater than VGS minus VTN. Okay, for PMOS transistor, it is just the opposite. So wherever you have a greater than sign, you will have a less than sign, and wherever you have a less than sign, you will have a greater than sign in the case of PMOS transistor. Okay, so now cutoff for NMOS cutoff region is when VGSN is less than VTN. So here VGSN is nothing but Vin, so Vin must be less than VTN. Then NMOS will be in the cutoff region. For linear, you have this is greater than, so you have this condition. Similarly, you have another condition, VDSN must be less than VGSN minus VTN. VDSN is nothing but Vout, and VGSN is nothing but Vin. So the condition becomes Vout must be less than Vin minus VTN. For saturation, the same conditions with the, here only this operator is inverted. Okay, it is instead of less than, you have greater than. And now when you come to PMOS transistor, as the voltage relationships are little different. Okay, we have some expressions there. Okay, so now VGSP is should be greater than VTP. VGSP must be greater than VTP. This is the condition. Okay, and for cutoff, so VGSP is nothing but Vin minus VDD. Okay, so Vin minus VDD must be greater than VTP, and now Vin is the variable here, so Vin must be greater than VTP plus VDD. So this is the condition for cutoff of the PMOS transistor in the CMOS inverter circuit. Okay, in the CMOS inverter circuit. Similarly, for linear region, you can write the equation and replace VGSP by Vn minus VDD and write it with respect to Vn, because Vn is the variable here. We are going to vary Vn. Okay, that is the variable here. Similarly, you have one more condition, VDSP must be greater than VGSP minus VTP. So VDSP is nothing but Vout minus VDD. So taking Vout and VDD to the other side. Okay, we already have Vin minus VDD for this, minus VTP plus VDD. Okay, so this 2 VDD get cancel. So Vout must be greater than Vin minus VTP. So these are the conditions, and here the same condition with the opposite relationship. Okay, so these are the relationship between the voltages and the three regions of operation of the transistor in a CMOS inverter circuit. Okay. Now, what is voltage transfer characteristics? So, voltage transfer characteristics is nothing but the relationship between the Vin and Vout of a CMOS inverter. Okay, or for any circuit, the relationship between Vin and Vout can be called as the voltage transfer characteristics. So, now our objective is to find out this for the CMOS inverter. This can be done analytically. Okay, you can write equations and solve it, and it can be done graphically, or it can be done by simulation. Okay, so by simulation you have already done it in the lab, and we are going to graphically, analytically, going to be little, you have to put little work on this. Graphically is little bit easy to understand, and we can easily do the graphical derivation of your voltage transfer characteristics. Okay, so now we will do the graphically, we will prove the voltage transfer characteristics. So now for a given Vin, Vout is found subject to the condition in this voltage transfer characteristics. Our only condition is IDSN is equal to IDSP. Otherwise, IDSN is equal to mod of IDSP. So we will find Vout for with the condition that IDSN is equal to IDSP. Okay, and now assume that VTN is equal to VTP. That is, the threshold voltage of the NMOS transistor is equal in magnitude. Okay, so if for the NMOS transistor I have my 0.5 as my what is the threshold voltage, for the PMOS transistor it will be minus 0.5. The threshold voltage will be minus 0.5. So we are assuming this. We are assuming symmetrical transistors, and we also assume that the PMOS is 2 to 3 times wider than the NMOS, so that beta n is equal to beta p. Okay, so you have a WL ratio which makes your P transistor to conduct more, or the mobility is increased. Mobility is increased by increasing the width of the P transistor, so that beta n is equal to beta p. So under these two assumptions, we are doing the voltage, deriving the voltage transfer characteristics. Okay, now let us just recall the current equations. Okay, we are not using this here, but for analytically or in higher classes, we will use these equations. Okay, anyway, recall that in a linear region, IDS is given by beta into VGS minus VT, V into VDS minus VDS the whole square by 2. Okay, we have derived it with respect to N transistor. The same is applicable for P transistor also. Okay, and in saturation region, we have IDS is given by beta by 2, VGS minus VT the whole square. Okay, so these equations, if there is time, we can you will be using these equations for deriving the threshold voltage of the inverter. Okay. Now to derive the voltage transfer characteristics graphically, the drain characteristics of NMOS and PMOS are drawn separately. Okay, assume that we have already assumed that they are symmetrical transistors. Okay, their threshold voltages are same but with the opposite polarity. Okay, and the beta n and beta p, the beta n and beta p are also same. Okay, so let us draw the drain characteristics. Drain characteristics is nothing but VDS versus ID. So these characteristics of both the transistors are drawn. So VDS versus ID characteristics are symmetrical, and they place themselves in the first and the third quadrant. So for NMOS, we have our characteristics in the first quadrant. VDS is positive and ID is positive. And for PMOS, you give a negative voltage at the drain. So VDS is negative. It's a negative voltage. Okay, drain is P type. So you give a negative voltage to attract your holes. So it is a negative voltage, and the current is in the opposite direction. So current is also negative. So the curves are appearing in the third quadrant. Okay, so this is the VDS versus ID plot of both NMOS and PMOS transistor. So for NMOS transistor, we have them in the first quadrant. Okay, and for PMOS transistor, we have them in the third quadrant. Okay, so this also you have already drawn this in your laboratory classes. So now we have taken different values of VGS. So VGS is equal to 0 volts. Okay, cut off, the current is 0. And then VGS N is equal to 0.6 volts, 0.9 volts, 1.4 volts, and 1.8 volts. This is the maximum. We are assuming a transistor in the 180 nanometer technology. So for 180 nanometer technology, VDD will be 1.8 volts. So we need to change VGS from 0 to 1.8 volts. So you get the family of curves. Okay. So now this region is, now this is the cutoff, and VGS is 0. And then VGS is 0.6, okay, around 0.4 or 0.5 will be your threshold voltage. So if VGS is 0.6 volts, there will be conduction, and there will be a linear region, and then the current becomes constant. And similarly, you have a linear region for every curve, and then the current, there is a pinch off, and the current becomes constant here. Okay, so the current increases with respect to VGS. And similarly, you have the curves marked here for PMOS transistor. So for PMOS transistors, when VGSP is equal to 0 volt, um, it is in the cutoff region. And then when VGSP is minus 6 volts, okay, let VTP, the threshold voltage of the P transistor, be minus 0.4 or minus 0.5 volts. Okay, so when you give VGSP is equal to minus 0.6 volts, it will start conducting. Okay, so you will get a current. So now this is more negative. VGSP is more negative than your VTP. Okay, similarly, when VGSP becomes more negative, it starts conducting, and you are getting a set of curves like this. Okay, so now after drawing these two family of curves, okay, what we are going to do is we are going to redraw the PMOS characteristics with respect to Vin instead of VGSP. Okay, so in the previous diagram, we have your the curves with respect to different values of VGSP. Now this VGSP has some relation with Vin. Okay, what is VGSP in terms of Vin? VGSP is equal to Vin minus VDD. Okay, so Vin is equal to VGSP plus VDD. Okay, so this is the relation. So now we are going to draw these curves with respect to Vn instead of VGSP, and at the same time we are going to take the absolute value of IDSP. Okay, IDSP is negative. Now we are going to take the absolute value so that it becomes positive. Okay, so now what happens? The current becomes positive. It goes to the positive y-axis. Okay, the current is positive y-axis. So take IDSN is equal to mod of IDSP, and then VGSP will be Vin minus VDD. So Vin will be equal to VGSP plus VDD. So using this relation, we will find Vin for different values of VGSP. Okay, so now we have curves for 0 volts, 0.6 volts, for when you see here VGSP is equal to 0 volts, minus 0.6 volts, minus 0.9 volts, minus 1.4 volts, and minus 1.8 volts. Okay, so now using the relationship, so if VGSP is equal to minus 1.8 volts, okay, what will be Vin? Vin will be VGSP plus VDD. Okay, so it will be VG minus 1.8 plus VDD. VDD is plus 1.8. So I'll get 0. That is, if VGSP is minus 1.8 volts, that means I have given an input voltage of 0 volts. In other words, when the input voltage is 0 volts, I get a voltage between the gate and source of my P transistor as minus 1.8 volts. Okay, that is the meaning. We are giving only Vn. We are not giving VGSP. Because of Vn, we are getting VGSP. Okay, so if Vn is equal to 0 volts, VGSP is going to be minus 1.8 volts. Okay, so the curve here, the curve which is here with the maximum negative current. Okay, now we have taken the mod of the current. We are making the current positive. So it will go to this, or it will go to the second quadrant, and now we are writing it with respect to Vin. So VGSP is equal to minus 1.8 refers to Vin is equal to 0 volts. Okay, I hope you all understand this. Okay, so we are rewriting the VGSP in terms of Vn, and we are taking the mod value of the current. Okay, so that's why the curves which are here, it is coming over here, the same curves. It looks like a mirror image or mirror image. Okay, from with respect to this negative x-axis. Okay, similarly, when VGSP is equal to minus 1.2 volts, the next curve in the family. So Vn will be VGSP plus VDD. So minus 1.2 plus 1.8 is equal to 0.6 volts. Am I right? Yeah, 0.6 volts. Similarly, when VGSP is equal to minus 0.9, we'll get plus 0.9 volts. Vin will be equal to plus 0.9 volts. Similarly, VGSP is equal to minus 0.6, Vin will be equal to 1.2 volts. When VGSP is equal to 0 volts, I'll have 0 plus VDD will be equal to 1.8 volts. Now, the curves have come here. So, this one refers to Vin is equal to 0. Next one is 0.6 volts, Vin is equal to 0.9, Vin is equal to 1.2, and Vin is equal to 1.8 volts. So this is the second step in the graphical method. Okay, and now we are solving this for Vn for Vn of n type to Vn of p type. Okay, so we have found out these two, and when IDS is equal to IDSN is equal to IDST. So this is how it's solve and find out the intersection points. Okay, so now we are going to intersect these curves by superimposing the PMOS curve on the NMOS curves. Okay, so we are going to move the curves from the second quadrant to the first quadrant, and we are going to intersect them and get the superimpose them, and we'll get some intersection points with respect to Vn. Okay, and we will find out a point. That particular point will refer to your VDS N, which is nothing but V out. Okay, so let us see in this diagram. Okay, so now I am intersecting two curves here. Okay, so now this horizontal red color curve line is for VGSN is equal to 0 volts. So VGSN is equal to 0 volts. That means Vn is equal to 0 volts. Okay, so this is the curve. When Vn is equal to 0 volts, the N transistor is not conducting or cut off, so the current is 0. Okay, now if Vn is equal to 0 volts, I have a curve for the PMOS transistor which goes like this. Okay, which goes like this. So now if I bring it here, okay, if I move it here, it will be coming like this. Okay, that's what we are seeing here. So it will be, I am superimposing this. So now this curve and this curve, they intersect at this point. Okay, so I get a point here. So what is the input voltage? 0 volts. Now what is the output voltage? Output voltage is VDSN, isn't it? VDSN is nothing but the output voltage. So what is the output voltage? I get 1.8 volts. It's nothing but VDD. So if Vin is equal to 0 volt, Vout is equal to, okay, this axis. So Vout is equal to 1.8 volts. Otherwise we have to see the points with respect to the this axis, y axis, okay, V out axis. So this is VDD. So we are getting 1 point over here. Now take the second curve and intersect. So the second curve is Vn is equal to 0.6 volts. So Vn is equal to 0.6 volts for N transistor. This is the curve, and for P transistor, this is the curve. Okay, where do they intersect? They intersect at another point here. Okay, which is, so this point refers to V out, which is slightly less than VDD. So I get a point over here. So what is Vn? Vn is 0.6 volts. Okay, just above 0 volts, 0.6 volts, and we are getting a voltage which is almost nearer to VDD. Okay, so for a low input voltage, we are getting a high output voltage. For 0 input voltage, we are getting VDD itself. For a low output voltage, we are getting this voltage. So similarly, we have to overlap all the curves. So N and P curves are superimposed and the intersection points are marked. So now if I mark the corresponding intersection points, here is 1 point, here is 1 point, here is 1 point, here is 1 point, here is 1 point. Okay, so now this point refers to Vn is equal to 0.9 volts. So for 0.9 volts, I am getting a voltage here, and this point refers to Vn is equal to 1.2 volts. So if Vn is equal to 1.2 volts, my output reduces, falls down. Okay, the output is this axis, so it comes near 0, and now Vn is equal to 1.8 volts. Okay, I have a horizontal green color line curve which is for PMOS. So this curve, and I have curve, it goes like this, up like this. So now this one, this red curve and this horizontal curve, it intersects at the point of origin. So I am getting a 0 output, 0 volts here. So if Vin is 1.8 volt, the output is 0 volts. This is the meaning of this. Okay, so you have got the points, the intersection points, they refer to the same current and the same Vin, right? Okay, because why same current? Because this one, if I take a point, the current is this is IDSN, which is equal to minus IDSP. Okay, so same current point and also the same voltage, input voltage point. Okay, so these points will give you the voltage transfer characteristics. Now we are taking these points and we are putting it with respect to V in versus V out. Okay, so this is your voltage transfer characteristics. So in the x-axis you have your V in and y-axis V out. So if V in is 0, okay, we have got V out is 1.8 volts. That's why we saw here. So if V in is 0, V in is 0, the output is 1.8 volts. So that one we have drawn here, this one. Okay, and then when Vn is equal to 1.8 volts, the output is 0, and we are having some intermediate points, and the voltage transfer characteristics will have a shape like this. Okay, so it will remain high for some time and it will fall down, the output will fall down, and there is a crossover, and it will again, when the input is high, the output will be low or 0. Okay, so now this is the actual curve, a typical curve, an ideal curve, and it is from Westy. Okay, so now you have Vn, you are dividing the voltages 0 volts, and the next voltage is called as VTN. Okay, the threshold voltage of the N transistor, and then the middle point is VDD by 2. And there is another point which is called as VDD minus VTP. Okay, so minus VTP is, or VDD plus VTP we can give, or minus mod of VTP. So VTP will be this is 0.4 volts, means this will also be 0.4 volts. So VDD minus 0.4 volts. There is another point, and this is the VDD by 2. So for a symmetrical transistor CMOS inverter, we have a curve like this where we have a sharp crossover, okay, sharp transition, and these are the regions of the voltage transfer characteristic curve. Okay, so now we'll see what does ABCD means. Okay, with that I think we'll end. Okay, and there is another interesting curve, okay, which gives you V in versus IDD, the current. Okay, so now if when V in is equal to VDD by 2, we will see that both the transistors are on or both the transistors are in saturation. So we'll have the highest current in both the transistors. So the current reaches a maximum when when Vn is equal to VDD by 2. That is in the cross point. This region we have the maximum current flowing through the circuit. Okay. So now these are the operating points. Okay, a very very interesting analysis. But we are not extending the analysis, okay, to all the regions. Actually, we have to find out the different points using these regions. Okay, we are not doing that because it's out of the scope of your syllabus or for your class. So they will be, the MTech students will be deriving this with respect to the statement. But anyway, you have to know the different regions of operation for a CMOS inverter. Okay, so now both NMOS and PMOS are there in the CMOS inverter, and the different operating point in the different region. Now this is your voltage transfer characteristics. This is the characteristics. Okay, and now we have divided the region from 0 to VTN, the threshold voltage of the N transistor, and then up to VDD by 2. Okay, and then VDD minus VTP. Okay, and then VTP. Okay, so now when your input is between less than VTN, your output will be high. It will be equal to VDD. This region is called as A region. Okay, and when your input is slightly greater than the threshold voltage, about 0.5, 0.6, 0.7, and then there is a the logic level is high, but there is a fall in your output voltage. Okay, so it begins to fall, and if you increase your input voltage to VDD by 2, okay, there is a sharp transition, so crossover, the output becomes less. Okay, and when you reach this point VDD minus VTP, it becomes 0, and then after that the output is 0. Okay, so if the input is increased, the output is 0. Okay, now so in these regions, what happens to the N and P transistors in region A, region B, region C, D, and E? Okay, so now we have to check this. We have a table. So I'll just justify the table and finish. Okay, so now we have to draw two lines here. We know the conditions for the NMOS transistor and the PMOS transistor to be in the saturation and in the saturation region and saturation region. Okay, so now in order to identify when they are in the saturation region, when they are in the not in the saturation region, we are drawing a line. Okay, so now what is the condition? NMOS is in saturation if Vn is greater than Vtn. Okay, that is VGS. VGS is nothing but Vn here. So when Vn is greater than Vtn, and there is another condition, VDSN must be greater than or equal to VGSN minus Vtn. Okay, so now VGSN is nothing but Vn, so VDSN is nothing but Vout, so Vout must be greater than Vn minus Vtn. Okay, so these two are the conditions. So Vn must be greater than Vtn, so Vn must be okay. And now see this diagram. This is 0. Okay, VTP is negative, so VTP will be somewhere here. Mark VTP also. And then VTN, let it be 0.4 or 0.5. Okay, so it is here. And then VDD by 2 is here. And then VDD minus VTP or plus VTP. Okay, it is here. Okay, so now this is VTP, this is VTP, this is VTN. And now Vn must be greater than Vtn. Till that it will be in the off condition. So if I draw a line here, it will be in the off condition, right? Which one? NMOS will be in the off condition. Okay, so till Vtn, it will be in the off condition only. Okay, and when Vn is greater than Vtn, when Vn is, this is your Vn, okay, this axis is Vn. So when Vn is greater than Vtn, it starts conducting and it will be in the linear region. But it may go to the saturation region if Vout is greater than Vn minus Vtn. Now, this is Vout, this axis is Vout. So, I can draw a line Vn minus Vtn. So, Vout is equal to Vn minus Vt. Vout is equal to Vn minus Vtn. This line, this is a straight line like this. This is the equation of the Vn minus Vout is equal to Vn minus Vtn by Y is equal to Mx plus C. Where this is the cutoff point, or what is it? We'll say that the point where it cuts the x-axis. Okay, so here it cuts at this point and it is not plus, it is minus. So Vn minus Vtn will be the equation of this line. Your condition is your output must be greater than that. Okay, so your output must be, so if I draw a line like this, the region above this will be the region for NMOS and saturation. So this blue region, okay, or the region which is above this line, what line? Vout is equal to Vn minus Vtn. So when it is greater than that, the NMOS will be in saturation. So this region is in NMOS and saturation. In this region, NMOS is in cutoff because your input voltage is less than Vtn. Okay, so draw a line Vn minus Vtn. The region above that is the region where NMOS is in saturation. Okay, now for PMOS in saturation, the condition is VGSP must be less than VTP. Opposite, the relational operators are opposite. Must be less than VTP, and VDSP must be less than or equal to VGSP minus VTP. And applying the a relation with respect to the CMOS inverter circuit. Vin must be less than VDD plus VTP and Vout must be equal to Vin minus VTP. So Vin must be less than VDD minus VTP. So draw a straight line for VDD plus VTP. This is the point VDD plus VTP. Okay, Vn must be less than that. So if it is greater than that, PMOS will be off. Here PMOS will be off. Definitely it will be off because your Vn is greater than VDD plus VTP. So this region PMOS is off. You will get a 0 output here. PMOS is cut off. Okay, so you will not get VDD. You will get something from your N transistor only. So here the output is 0 definitely. And now for saturation region, in this region you have Vout must be less than Vin minus VTP. So now this is the line Vin minus VTP. Okay, so this line and your condition is Vout must be less than that. So you have a region which is below this line. So that line will give you PMOS is in saturation. So you only blue color, it means NMOS is in saturation. This color, brick color, PMOS is in saturation. And this region, the intersection region, both are in saturation. So the point C or the transition happens when both the transistors are in saturation. Okay. So according to this, now you have your, regions of CMOS inverter operation. So in region A, okay. What is the region A? Vn is greater than 0 but less than Vtn. So N device will be in cutoff. Okay. P device will be in linear. Okay. Let us see how. So let Vn is equal to 0.4. Let your threshold be 0.5 volts and now Vn is equal to 0.4 volts. Okay. So what is VGSP? It is Vn minus VDD. So 0.4 minus 1.8. So it is minus 1.4 volts. VTP is minus 1.4 volts. Okay. So the condition for PMOS conducting is, or PMOS on is, VGSP must be more negative or it must be less than VTP. So VTP is minus 0.5 volts and VGSP is minus 1.4 volts. So naturally PMOS would be in the conducting states. Okay. So PMOS is conducting and it is on. Okay. And it is in the linear region, not in the saturation region. For similar, if you put an example and analyze that, we will see that the other condition for saturation for PMOS is not satisfied. Okay, so P device is in linear. Okay, hope you understood this. VGSP is minus 1.4 volts, which is less than minus VTP, or it is VGSP is more negative than your threshold voltage. So PMOS is conducting. Okay, so PMOS is in the linear region and N device is in the cutoff region. And then in region P, PMOS is in linear region and NMOS has come to the saturation region. Now you have to use your diagram. Okay, diagrammatically, graphically, we have drawn the lines of saturation. Okay, the water lines of saturation. So above and below which these transistors are in saturation. Okay, so this B is in saturation for N transistors. So N device is in saturation. And then Cn is the region where both the transistors are in saturation. Similarly, D. Okay, similar regions. P is in saturation, N will be in linear, and in E, P is definitely in cutoff, and N will be in linear. Okay, so we can substantiate this with some input values, Vn values, and find out the other voltages and the conditions, and we can prove it. Okay, so now you can remember this. In this table, and in A region, Vout will be VDD. And in B region, Vout will be greater than VDD by 2. And then see there is a sharp drop. And then D, Vout will be less than VDD by 2. And in E region, Vout will be 0. Okay. So now we have one term called as inverter threshold voltage. Okay. This is for the inverter circuit, which is called as a logical threshold voltage. So it is defined as the voltage, crossover voltage at which Vin is equal to Vout. Okay, this usually happens in the C region, in the transition region. So that is called as the logic threshold of the inverter. This can be analytically found, okay, but we are not doing this now. And this point occurs in the region C and hence can be derived by equating the current of both the transistors which are in saturation region at that region. Okay, symmetrical NNP transistors V inverter or V threshold will be VDD by 2. Okay, and let us finish by this last slide. So here some important features of CMOS inverter. We have many families, and CMOS inverter is special with it has some important properties like the high output will be equal to VDD and the low output will be equal to ground. Okay, so the voltage swing will be VDD minus 0 is nothing but VDD. Okay, so this results in a high noise margin. Okay, noise immunity will be more, noise margin is more, and noise immunity is also more. So the high and low outputs are exactly equal to VDD and 0 volts. This is a good feature of CMOS inverter. The input resistance is very high, equal to the gate resistance. And a single inverter can theoretically drive infinite number of gates. That means the fan out is infinite, and there is no direct no direct path between the supply and the ground rails under steady state operation conditions. That means there is no path between the ground and VDD. Hence, the static power is very less. Static power dissipation is very less. Okay, so these are the important characteristics of CMOS inverter. Okay. Students, so I hope you have all understood the CMOS inverter voltage transfer characteristic derivation, which is done graphically. Okay, this analysis is very important, and we haven't done it analytically, only graphically. I hope you all understood this, and if you have any doubts, you can approach me personally. Okay, all the best for your exam. Bye.